Imagine you are standing perfectly still. You feel motionless. The ground beneath your feet seems solid and unchanging, but you are not standing on something solid at all. You are standing inside something that can bend, stretch, and ripple like the surface of a pond. This something is not air. It is not matter. It is the very fabric that holds space and time together, and when that fabric moves, the entire universe trembles. This is not poetry, this is reality. Let us begin with a question that may seem simple, but carries within it one of the deepest truths about existence. What is gravity? Most people believe gravity is a force, something invisible that pulls objects toward each other. But this explanation, while useful, hides a far stranger and more beautiful truth. Gravity is not a force. Gravity is geometry. It is the shape of reality itself. Think of space and time not as separate things, but as a single, unified fabric. We call this spacetime. Imagine this fabric stretched out in all directions, smooth and flat when nothing is present. Now place a heavy object, say a star, onto this fabric. What happens? The fabric bends, it curves downward around the mass. The star does not pull on nearby objects with invisible hands. Instead, it warps the very space around it, and objects moving through that space follow the curves. They roll along the bends in space-time like marbles rolling around a dip in a stretched sheet. This is what gravity truly is. Mass tells space-time how to curve space-time. Tells mass how to move. There is no mysterious pulling force. There is only the geometry of existence responding to the presence of matter and energy. Now here is where reality becomes even stranger. If space-time can curve in the presence of mass, what happens when that mass moves? Imagine dropping a stone into a perfectly still pond. The stone displaces the water, and ripples spread outward in every direction. The ripples are disturbances traveling through the medium of water. They carry energy away from the point of impact. Space-time behaves in a remarkably similar way when massive objects accelerate, when they move violently or orbit each other at tremendous speeds. They shake the fabric of space-time itself. And just like ripples on a pond, disturbances spread outward from the source. These disturbances are not made of matter. They are not particles. They are waves in the geometry of space and time. We call them gravitational waves. Let us picture this more carefully. Imagine two massive stars orbiting each other, locked in a cosmic dance. Each star sits in a deep well of curved space-time. As they orbit, they do not simply glide smoothly around a static curve. Their motion creates changing distortions in the fabric around them. These distortions do not stay locked in place. They ripple outward, spreading across the universe at a very specific speed, the speed of light. Why the speed of light? Because nothing, not even disturbances in space-time itself, can travel faster than light. This is a fundamental rule of reality. Light does not simply move quickly. Light moves at the maximum speed that causality, the very structure of cause and effect, permits. Gravitational waves obey this same cosmic speed limit. Now, what would it feel like if a gravitational wave passed through you? It would not push you sideways. It would not knock you over. Instead, it would very briefly change the distances between points in space. Imagine you are standing with your arms outstretched. As the wave passes, the space between your left hand and your right hand would oscillate, stretching and squeezing by an almost unimaginably tiny amount. Then the wave would pass and everything would return. Too normal. You would not feel this. The effect is far too small for human senses, but with the right instruments it can be measured. These waves carry information. When two black holes spiral into each other, merging in a violent collision far away in the universe, they release tremendous energy in the form of gravitational waves. The waves spread outward like invisible ripples, crossing vast distances, traveling through galaxies, through the emptiness of space, carrying with them a record of the event that created them. If you could detect these waves, you could learn about events happening billions of light years away, events no telescope could ever see because they produce no light. Let us think about why these waves exist at all. The answer lies in a principle we can call the dynamic nature of fields. Imagine you have an electric charge. If the charge sits perfectly still, it creates an electric field around itself, but this field does not radiate energy away. Now move the charge back and forth, accelerate it, and something changes. The changes in the field cannot update instantaneously everywhere in space. Instead, they propagate outward as electromagnetic waves, waves of light. The accelerating charge loses energy by radiating these waves. Gravity works in a similar way, but with an important difference. A single mass sitting still curves spacetime, but this curvature is static. It does not radiate. Even a mass moving at constant velocity does not radiate gravitational waves. The key is acceleration, and not just any acceleration. The mass distribution must change in a way that is asymmetric, that lacks perfect spherical symmetry. A perfectly spherical star pulsing in and out symmetrically does not radiate gravitational waves, but two stars orbiting each other do, because their combined mass distribution changes in an asymmetric way as they circle. When these waves are produced, they carry energy away from the source. This means the orbiting stars lose energy, and when a system loses energy, it changes. The two stars spiral closer together, their orbit speeds up, they radiate even more gravitational waves. The process accelerates. Eventually, if the stars are dense enough, compact enough, they merge. And in that final moment, the collision releases an enormous burst of gravitational waves, a signal so powerful it can be detected across the universe. Now let us pause and appreciate something remarkable. These waves are not made of particles. They are not made of matter or light. They are pure geometry in motion. When we say a gravitational wave passes through a region of space, we mean that the distances between points in that region oscillate. The metric, the very rule that tells us how to measure distances and times, fluctuates. Reality itself vibrates. Think of a ruler. Normally, we think of a ruler as defining distance. But what if the ruler itself could stretch and shrink as you used it? That is what a gravitational wave does. It does not move objects through space. It changes the space those objects occupy. This is why detecting gravitational waves requires such extraordinary precision. The changes in distance are incredibly small. When a gravitational wave from a distant cosmic event passes through Earth, it might change the distance between 2 points separated by several kilometers by less than the width of a single atomic nucleus. Detecting such a change requires instruments of almost inconceivable sensitivity. But the principle is clear. Space-time is not a fixed stage on which events unfold. Space-time is dynamic. It responds to mass and energy. It can ripple, wave, and carry information across the cosmos. Understanding this changes how we see the universe. We are not observers standing outside of space and time, looking in. We are participants, embedded in a fabric that bends, stretches, and vibrates around us. Let us consider what this means for the universe as a whole. Every violent event in the cosmos, every collision of dense stars, every merger of black holes, every supernova explosion with the right kind of asymmetry sends out gravitational waves. These waves travel outward, passing through galaxies, through clouds of gas and dust, through planets and stars, mostly unimpeded, unlike light, which can be absorbed or scattered. Gravitational waves interact very weakly with matter. They pass through almost everything. This means they carry information from the depths of events that light cannot escape, from regions hidden behind dense matter, from the interiors of the most extreme objects in the universe. Imagine a black hole. By definition, nothing can escape from inside its event horizon, not even light. But when two black holes merge, the event happens outside the horizons, in the curved spacetime around them. Gravitational waves are produced. Those waves escape, carrying information about the masses, the spins, the final shape of the merged black hole. In this way, we can learn about objects that are otherwise completely invisible. This tells us something profound about the nature of reality. The universe is not silent. It hums with the vibrations of space-time itself. Every massive event leaves an imprint, a signature written in the geometry of existence. We live in a universe that has memory, that carries records of its most violent and energetic moments encoded in ripples spreading outward at the speed of light. Now let us return to the question of why these waves behave the way they do. The answer is connected to the constancy of the speed of light, a principle that governs all of reality. In special relativity, we learned that the speed of light is the same for all observers, no matter how they move. This leads to the unification of space and time into space-time. In general relativity, we extend this idea. Space-time is not just a passive container, it has structure. It can curve, and changes in that curvature propagate at the speed of light. So why? Because if changes in gravity, changes in the curvature of spacetime could propagate instantly, faster than light, it would violate causality. It would allow information to travel backward in time. The universe does not permit this. The structure of spacetime itself enforces the cosmic speed limit. Gravitational waves obey this limit because they are disturbances in spacetime, and spacetime respects its own rules. Think about what this means when two stars orbit each other. At any given moment, each star responds not to where the other star is now, but to where it was a short time ago, the time it takes for gravitational influence to travel between them. For nearby objects, this delay is insignificant, but the principle is absolute. Gravity is not instantaneous, it propagates, and when it propagates in the form of waves, those waves carry energy and information across the cosmos. Let us also consider the symmetry of nature. In physics, symmetries are deeply important. They tell us which quantities are conserved, which laws remain unchanged under transformations. Gravitational waves emerge from the symmetries and dynamics of general relativity. The equations that describe the curvature of spacetime admit wave-like solutions. These solutions represent ripples traveling through the fabric of reality. The mathematics is elegant. The physical interpretation is profound. When we solve these equations carefully, we find that gravitational waves have a specific character. They oscillate. They have a frequency, a wavelength, an amplitude. They can be polarized in specific ways, stretching space in one direction while compressing it in another, then reversing. They carry energy, and this energy must come from somewhere. It comes from the orbital energy of the objects creating the waves. As the waves radiate away, the orbit decays, the system evolves. This is a beautiful feedback loop. Motion creates waves. Waves carry away energy. Loss of energy changes the motion. Now imagine the universe filled with these waves, mergers happening in distant galaxies, black holes colliding, neutron stars spiraling together. Each event sends out its signal. The waves pass through each other, through us, through everything, mostly unnoticed but always present. The universe is alive with gravitational radiation, a symphony of space-time vibrations playing constantly in the background of existence. This brings us to a question of perspective. How do we know gravitational waves are real? We know because the mathematics of general relativity predicts them with precision. The equations are not ambiguous. They describe a universe where spacetime is dynamic, where curvature can propagate, where ripples are inevitable. The theory makes specific predictions. It tells us how strong the waves should be, how fast they should travel, how they should interact with detectors. And when we build instruments sensitive enough to measure them, when we observe the universe carefully enough, we find exactly what the theory predicts. This is how science works. We start with principles, with observations about reality. We build a mathematical framework that describes those observations. We use that framework to predict new phenomena. Then we test those predictions. When the predictions are confirmed, our confidence in the underlying principles grows. Gravitational. Waves are a triumph of this process. They were predicted by theory long before they could be observed. They are a consequence of taking seriously the idea that gravity is geometry, that spacetime is real, that the universe follows mathematical laws. Let us think about the energy these waves carry. When two massive objects merge, an enormous amount of mass energy is converted into gravitational waves. Remember the relationship between mass and energy. They are equivalent, two forms of the same thing. When black holes collide, a significant fraction of their total mass can be radiated away as pure gravitational wave energy. This energy does not disappear. It spreads through the universe, stretching and squeezing space-time as it goes. Eventually, the waves become so weak, so diluted by distance, that they are barely detectable, but they never truly vanish. They continue propagating, carrying their message across cosmic time. This raises a beautiful point. The universe has a history written in waves. Every major event leaves a trace. If we could detect all the gravitational waves passing through us at any moment, we could reconstruct a record of violent cosmic events going back billions of years. We would see a history of the universe told not in light, but in the geometry of space-time itself. Now, let us reflect on what all of this means. We live in a universe far stranger than it appears. The space around us is not empty. It is not static. It is a dynamic, flexible fabric that bends under the weight of matter, that ripples when matter moves. Time is not separate from space. They are woven together into a single entity that responds to the presence of energy. And when that entity is disturbed, when massive objects accelerate, the disturbances spread outward as waves, carrying information, carrying energy, connecting distant parts of the universe in a profound and beautiful way. Gravitational waves teach us humility. They remind us that reality operates on scales and with subtleties far beyond our everyday experience. The changes they produce are so small, so delicate, that it took humanity a century from their prediction to their detection, and yet they are real, they are measurable, they are a fundamental part of how the universe works. They also teach us wonder. The universe is not a cold mechanical system. It is a living, breathing tapestry of space-time, vibrating with the echoes of cosmic events. Every massive collision, every spiraling pair of stars, every burst of energy sends out its signal, and if we listen carefully, with the right instruments, with the right understanding, we can hear the universe speaking to us in the language of geometry. This is the power of understanding reality deeply. We move beyond surface explanations. We see that gravity is not just a force that makes apples fall. It is the curvature of existence. We see that space-time is not just a backdrop. It is a participant in every event, responding, rippling, carrying information. We see that the universe is unified, that the same principles govern the fall of a stone and the merger of black holes billions of light years away. And perhaps most importantly, we see that the universe can be understood. It follows rules. It respects logic. It reveals itself to those who ask the right questions and pursue them with honesty and rigor. Gravitational waves are not magic. They are physics. They are the natural consequence of a universe where space and time are real, where geometry is dynamic, where matter and energy shape the very fabric of existence. So when you stand still and feel the ground beneath your feet, remember, you are not standing on something separate from space and time. You are standing inside space-time itself, and at this very moment, gravitational waves from distant cosmic events are passing through you, through the Earth, through the solar system, stretching and squeezing the fabric of reality by amounts too small to feel but real nonetheless. The universe is speaking, and now we have learned to listen.